Section 7, we're going to take a look at hyperbolic functions. Now, there are certain even and odd exponential functions, e to the x, e to the x, and e to the negative x, that they come up so frequently in mathematics and other applications that they have a special name called the hyperbolic functions. Now, just like we have trig functions that relate to circles, right? We have trig functions that relate to circles, and that same way that relation is the same relation with these hyperbolic functions relate to the hyperbola. So hyperbolic relate in that same way that trig functions do to circles, as hyperbolics relate to the hyperbolic functions relate to hyperbolas. If you can remember from trig, the hyperbola looks something like this. We have basic x squared if it starts at the center, and a y squared, like a circle, equals 1. But a hyperbola is the denominators are a little bit different, where it's a squared and b squared. But other than an ellipse, like this would look kind of like an ellipse a little bit, except for we have subtraction here, and that's what makes a hyperbola. And so a hyperbolic function, the relation between e to the x's, these relationship between these two functions, hyperbolic function, which is called the hyperbolic function, it relates to the hyperbola, which kind of looks like that. And like that. Or like this. So either like that or like that. That's what a hyperbola looks like. So hyperbolic's going to have that same kind of thing going on. And so these are the hyperbolic functions. Now, a little bit written in here. You have sine, kind of sine of x. You have this h in here. It stands for hyperbolic. So this is how you read it. Oops. Hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. That's how you read those. All right, and then these are what they equal. Like we said before, it's some relationship between e to the x and e to the negative x. That's the best way to describe them. So hyperbolic sine looks like this. Hyperbolic cosine, difference is subtraction and adding. And then hyperbolic tangent, like sine over cosine, just like normal sine over cosine for tangent. Okay? And so if you normally look at those equations, here's sine right here. So if I graph these two separately, and that's where this green one is, and red one. So it's kind of hard to see, but let me go ahead and take off. So that's what hyperbolic sine looks like, because e to the x would look something like this, and e to the negative x would look something like this, right? So the hyperbolic sine, because I'm subtracting between them, it's the difference of them, so it takes on this shape right here, without that crazy squiggly thing there. Okay, let's see. Oops. Then cosine would be adding those two, so let's go ahead and take that out. So here's cosine. That's what cosine would look like, because it's the addition of those two. And then here's what tangent looks like. And tangent is in between plus or minus 1. So we have this equation, y equals positive 1 that runs through here, and minus 1. So the tangent 1 runs in between these two, like that. So those were what the graphs look like for those three. So there's tangent, here is sine, and then here is cosine. So those are the three looking graphs of hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. So here's some things that kind of come up in the different applications is if you have a catenary, which is if you have two telephone poles and the wire in between those, then you can go ahead and find, so this wire hanging in between two telephone poles, the shape of it can be explained by this hyperbolic equation of cosine right here. That's usually the most famous one. It also occurs, you can have hyperbolic equations uh, with dealing with light, dealing with velocity, electricity, radioactivity. And here's another one, velocity of a wave. So that can be explained by a hyperbolic function tangent. So those are some applications that these hyperbolic functions come up in. And then here is some hyperbolic identities. So hyperbolic sine is an odd function, meaning if I have negative x, then the answer would be negative whatever the original hyperbolic sine is. Where hyperbolic cosine is even, meaning if I plug in a negative x, I will just get my original hyperbolic cosine. Okay, and then kind of same thing a little bit with um, sine and cosine, where there's the squareds equal 1, except for this is subtraction. And then we also have the tangent one, hyperbolic tangent, hyperbolic secant. And then we have the addition. Let me do a different color. Addition, and you could do subtraction as well for hyperbolic sine and hyperbolic cosine of two angles. It looks like this. Okay. All right, let's go ahead and go through an example real quick. Let's go ahead and prove that this is true. So we'll go ahead and square hyperbolic cosine. Well, hyperbolic cosine is e to the x minus e, or plus e to the negative x all over 2, minus hyperbolic sine, which is e to the x minus e to the negative x all over 2. And so we'll go ahead and square those. So we'll square the bottom, which is easy, 4. And we'll square this bottom, which is 4. Then if we subtract two fractions, it's common denominator. So really this is just a common denominator of 4. But then squaring the top is a little bit different. So we got to square e to the x plus e to the negative x times 2, right? So it's kind of like a plus b squared. Well, that's just a squared plus 2ab plus b squared. B squared. All right. Okay, so a squared would be just ex times ex, which when I multiply by the same base, I add exponents. So x plus x is 2x, so that'd be e to the 2x. Then I just have 2. There's no squared there. I just have 2ab, so that's plus 2. Ex times ex would be adding those x and negative x, which would give me 0x, so that's just 1. And 1 times 2 would just be 2. And then this would just be e to the 2 minus 2x, because it's negative x plus a negative x is negative 2x. And then subtract, doing the same thing here, except for here you get a minus, which would just leave the middle to be minus. So that'd be e to the 2x minus 2, and then plus e to the negative 2x. Okay, and then I can go ahead and distribute that negative. And I have e, let's just distribute it here. So minus, plus, minus. Okay, so then these can cancel out, right? This would turn to 4. This would cancel out with this one. So I just get 4 over 4, which equals 1. which equals 1. Okay, so that's how I proved that one. All right, now let's go ahead and prove this one. So 1 minus tan, hyperbolic tan squared equals hyperbolic secant squared. So we know this is just 1. We know this is hyperbolic sine over hyperbolic cosine. And this is just 1 over hyperbolic cosine squared. Okay, oh, and these are squared too. All right, so we need a common denominator, so that'd be cosine, hyperbolic cosine squared x over hyperbolic cosine squared x. So then we can combine those, and we just proved that this one is equal to 1, right? We just proved that is equal to 1. So then we get 1 over hyperbolic cosine squared, which we just see is that right there, which is that one. So there we just proved this statement as well. All right, so that'll be it for this video. So that's just kind of introduction of these hyperbolic identities and hyperbolic functions. But in the next video, I'll go ahead and go through the derivatives and proving some of those derivatives. But I guess I could go ahead and show you what those derivatives look like, and then in the next video, I'll go ahead and do some examples of actually solving them. So here are the derivatives of the hyperbolic functions. They're similar to the trigonometric ones, trig ones. So the derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. Derivative hyperbolic tangent is hyperbolic secant. Hyperbolic of cosecant is negative hyperbolic cosecant times hyperbolic cotangent, and then derivative hyperbolic secant is negative hyperbolic secant times hyperbolic tangent, and then the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. So those are all the derivatives of those. I decided to just do a few examples. So basically anytime other than it's just hyperbolic cosine or sine, other than just an x, then it's just going to be the u type, right? So we're just going to take the derivative of the outside. It's going to be chain rule times the derivative of the inside. So hyperbolic derivative hyperbolic cosine, and then leave the inside the same, and then times that by the derivative of the inside. Right, so it's just going to be chain rule. This is just to the 1/2, right? So the derivative of that would be 1/2 x minus 1/2, and then times by the derivative of hyperbolic cosine, which is hyperbolic sine. You leave that inside the same. So there we go. There's our answer. You can rewrite it maybe with this in front, and you could bring that down if you wanted to. So you could simplify this a little more with maybe something like this, all over 2x to the square root of x, like that. If you want to simplify it a little bit more. All right, so now I go ahead and call it good. But yeah, anytime it's other than just x in here, you're going to have to do chain rule, and you're used to that.